Epic. Epic! Epic Stat Tool 1 Speedruns of Statistics! Brian Stevens! Versus Chapter 15, Testing Hypothesis. Begin! Hey everybody, we are back. We're going to start another speed run right here. Let me get the right screen up and let me get the chat going. So just 1 second before we start this speed run. Sorry, we got to do a little bit of prep. Just ended the last one. I'm going to get there we go. Thank you for tuning in, it says. And we got 4 people watching. Say hey in the chat if you are here. Let me wake up Mewbot this time. He might have been awake last time. He might not have been awake. Who knows? Wake up Mewbot. Time to wake up right there. There we go. If you are here in the chat, feel free to say, hey, everything is good to go. We're going to put everything good on the screen, and Mewbot is waking up. Good to see you here, Carly and Megan. Throw some questions in the chat if something is not clear while I'm doing this epic speed run right here. This is the prep for the epic speed run right here. Good to see you here, Ashura. So awesome. Mewbot is awake, so you can always ask questions to Mewbot. He is awake now. Say hey, Mewbot.
I am Mewbot.
Good to see you here, Mewbot. So he does not exist in this world, though. Maybe I'll bring him over for the next speed run. Oh, well, welcome. Thank you, Robbie. We're going to cover these topics in this epic speed run. So here we go. Ask questions if you got them as I go through the topics. If I do not elaborate on something enough, let me know. We got 30 minutes for each. Check it out. Here we go. Okay, so this is all about testing hypotheses. And it comes down to what is testing a hypothesis? When we do statistics, we start out with an initial belief, and that initial belief is called the null hypothesis. And you're just going to think this is true to start. Like, you're just going to say, like, do you have a belief right now? Do you have anything you believe? Like, I believe there's milk in the refrigerator. And so, like, I believe that. But if Chelsea were to come in here and say, we really need milk, I'd be like, oh, I reject my null, or we're running low. I'd have evidence we're running low. Think about that right there. You have a belief in your head. That's what a null hypothesis is. It can be any belief you hold. I believe it is not raining outside right now. And so what would make me reject that belief if I start to hear rain against the window, things like that? That'd be evidence against that belief. But what if I'm wrong? Because we'll talk about errors in later chapters where maybe it's not raining. Maybe someone has a hose and they're spraying it up in the air and the rain is and the water is hitting the window. So a null hypothesis is just our starting belief. It's whatever you currently hold in your head that will be either continuing to believe after this, or we will reject and no longer believe. So when we do these nulls in statistics, we often use the equal sign. Let's just talk about writing a null hypothesis right here and how we write it in statistics. Like, let's say I were to believe that UT students spend $20 on snacks a week. So like, because like you go to the pod or something like that, or go to the student union, I really hope Vicky's still working in the student union. Shout out to Vicky right there. But she's so awesome. If you know her, say hey. Be like, Brian Stevens of Statistics says, hey, I really hope through all this craziness that she's still working there. See if you can figure out how to write the null hypothesis that students on average, on average spend $20 a week at the student union. So what would be the null hypothesis that students spend $20 a week on average at the student union? Well, if I'm saying on average, we're talking about the mean. So you're going to put the mean right here. And then you're going to put equals because the null always has the equal sign. I can't state that enough. The null always has the equal sign. And then you're going to put the hypothesized amount right here. Let's break this down the way it's written out. When you write out this null and alternative hypothesis, we'll write the alternative in a little bit. The first part right here is going to be the parameter of interest. So whatever we're analyzing is going to be the parameter. So you have other parameters you might put right here. You could put like the true proportion, or you could put the true difference between two means. All the options for this would be right here, and I'll write them right here. You can either put mu for this class, p, or mu1 minus mu2. These are all the options we put for this class. There are other things to put there, but for this class, when we do statistical notation this way, the only things that would go in this position right here for the parameter of interest that we're analyzing would be mu, p, or mu1 minus mu2. This is analyzing the true mean, like what is the GPA of UT students, how much do they spend at the pod. This is P, which is the true proportion, like what percent of students own a pet, what percent of students pass the class, things like that would be P. Here we have mu1 minus mu2, which is what is the true difference between two means, which is chapter 17 when we talk about like what's the difference between UT students and Florida students' GPAs, or what's the difference between on-campus and off-campus students and how much they spend on snacks. So then you're analyzing the difference between two means. We always have the equal sign, so don't worry about this. You always have the equal sign when writing it out in statistical notation. The last part right here is going to be the hypothesized value. So the hypothesized value can be anything. Sometimes it's a little bound. Like if we're doing proportions, it has to be between 0 and 1 because we can't. It'd be ridiculous to hypothesize a proportion of like point or 1.2 because you can't have a proportion outside of 0 and 1. But this is whatever we are saying we believe at the current moment. So the hypothesized value is just something we believe. So this is the hypothesized value. And I want to point something out. The hypothesized value is oftentimes going to be mu naught in notation, p naught. And technically this last one is delta naught, but a lot of times it's just 0. So relative to these right here, when you are talking about a mean, you hypothesize a mean. So that's the hypothesized mean. When you're talking about a proportion, you hypothesize a proportion. When you're talking about the difference between two means, you often hypothesize that the difference is 0. You're not required to hypothesize the difference is 0. But take a moment right here and see if you could answer this question. Are you ready? This is a test question for everybody. Brian wants to analyze, or Brian currently believes that, let's say 25% of students own a pet. What would the null hypothesis be? So see if you can figure out the null hypothesis from what I just showed you. See if you could be right here and figure out, okay, Brian's looking at do they own a pet or not? 25% of students own a pet. We could add more to this to add confusion. This has enough to write the null, but it could say he takes a sample of 200 students and finds out that 20% own a pet. There's a lot more to identify in this question right now, but the first part of it has enough. And the first part of it that has enough right here is going to be, we have here the hypothesized value, and we know that we're also testing, I think I did this one in blue, we are testing proportions because we're saying, do you own a pet? So the question, do you own a pet, would lead to proportions right here. So we have here P is what we're testing, and great job right there, Ella. And then we have here equals, because the null always has the equal sign. And then we have here the hypothesized value in proportion. This just says the null states. That's all that HO says. It's the null states that the true proportion of students who own a pet is 25%. Now, all I'm doing right here to write the alternative, which is what we'll talk about next, here, let's just show it on the screen to make it clear that we're switching topics, is we're just changing the sign. So the reason we spend so much time on focusing on how to write the null hypothesis is because if you know how to write the null, you can write the alternative. The only thing that changes about the alternative is going to be the sign. The only thing that changes about the alternative, try to do the same colors, is going to be the sign. It'll change from does not equals greater than or less than. So all we do is we go back to our original question that we wrote just a second ago, and we say, Brian wants to see if this is true. Well, I never say if we want to see more than this, less than this. I just say I want to see if that's true. So what would the alternative be? Well, the best way to write your alternative is to keep everything the same. Do not change this to p hat or anything. I see that a lot, that people change this. Do not change anything but the sign. So the only thing that changes here is I'm seeing if it's true, and now I'm going to see if it's not true. So the alternative is where we give our well, we want to see if it's equal to 25% or not equal to 25%. One of these things is what we're going to end up either continuing to believe or finding evidence for. And we could run this test right here. But when we do this right here, we need to have our initial belief, which is the null, and then we need to have our alternative that we're going to look to see if there's evidence for. And remember, the only thing that changes when you do this is the sign. My pens are haunted. The only thing that changes when you do this is the sign. And how do you know the direction of the sign? Well, the sign is going to be directed by the question itself. Is there evidence that less than 25% own a pet? Now we have a different sign right here. The sign now is going to be less than. Is there evidence for the alternative that the true proportion is less than? So when you're looking for the sign, make sure to look at the question. If the question doesn't give you any sort of inclination, use the does not equal sign. So a lot of times we like to phrase things as, is there evidence? Or they're testing the claim of this. The claim is always the alternative. So the alternative is always the claim-based one, where the null is the initial belief. So good stuff right there on the null and the alternative right there. So when we talk about one-sided or two-sided, one-sided and two-sided is going to merely be if we're doing a less than or greater than, those are the one-sided, or the does not equals is going to be the two-sided. When you do these tests, it looks the following way, and this is a good time to review this, how to do the p-values. The p-values for these, let's take a look, would be the following. If you run a test with a greater than alternative, you will shade to the right. So there is our test statistic, and here is our p-value. If you run a test with the, I'm going to go full screen. If you run a test with the less than alternative, you will shade to the left. We'll show that here in a second. We'll need to erase some stuff. I like to make them all look exactly the same. So here is the less than alternative. And let's shade that. And what do you notice about the greater than and the less than alternative? When you do the greater than and the less than alternative, you've shaded the whole curve. If I were to just bring this up here, you would shade the whole entire curve with the greater than and the less than. So it's important to know when you run these tests that these two p-values, like if this is 0.08, this one right here has to be 0.92. That means the probability of our results from our stream happening by random chance variation is 92%, and that is the p-value. These two p-values for the greater than, and look at the way the greater than points to the right, and the less than points to the left right there. They shade the direction they point from the test statistic you find when doing the test. I think the confusing one a lot of times is the does not equals alternative, but all you do is take and reflect the area on the other side. So we're literally going to take this area right here, put it right there, and then we're going to take the same area and we're just going to reverse it. Watch as we show this, because all we are doing is just reflecting it and putting it over here. So we would go to something just as extreme on this side, and just think about if I doubled that area, well, then the p-value for this would be 0.16. So the p-values right here have this relationship that the greater than and the less than always add up to 1. So if we were to add these two together right here, they always add up to 1. And then the does not equals is always times 2 of the smallest, because you're just reflecting it on the other side. And you can see this a lot of times in jump output. We can do a quick test right here. So let's go right here and go to test mean. I'm thinking, sure, let's go 4850, test mean, and we're going to test 4850. And if you look right here, it didn't turn out so perfectly, but 29 times 2 is going to be 58, and 100 or 1 minus 29 is about 71. This is the greater than alternative, which is greater than this red line. So from this red line over is 71% of the curve. From this red line right here to the right, let me make this way bigger so you can see it, and I'll disappear. From this red line over is 71%. From this red line to the left is 29%. And if you double it, you get the 58%, which is the two portions of this curve. So that is how we get these p-values right here. And there is the test statistic of -0.55, which is how many standard errors we are below the mean. We haven't covered that yet, but this is all about the p-values right here and how they're found and the relationship they have based on the alternative hypothesis we are doing. We've talked about this a little bit right here. Let me reappear. How to interpret a p-value. So back to speedruns. So let's talk about how to interpret a p-value. A p-value is going to be the probability of our results or results more extreme happening by random chance variation given the null is true. Hey, Hannah, good to see you here. Mubot is awake and points are being tracked. And if you have questions, let me know. I can expand upon things. We have two things to talk about right here. If you were to get a p-value over here, like let's say you believed that 25% of students owned a pet, and you were to see a result somewhere around like 38%, just an example. We haven't done the full calculations. and you get a p-value of this, which your p-value is going to be, let's say, 0.001. What is that telling you about your observed result, which would be a p-hat? Your p-hat, which is what you saw in your sample, you saw this right here. When you see this, this is telling you the probability of 38% of students owning a pet or more extreme would only occur 1 in 1,000 times in a sample given 25% of students actually own a pet. This is the null right here, which is at the center of the distribution. And if the null is true, which is what we might currently believe, then this would be super unlikely to happen by random chance. It's like, yeah, if it's true that 25% of students own a pet, then I doubt in a random sample I would see 38% of students owning a pet. This is super unlikely. I reject the null. And in this instance, we're testing the greater than alternative because we're shading to the right. I have evidence that more than 25% of students own a pet. But what if we could move this over right here, which we can do visually, and you saw something in a sample, because this is p hat right here, that was much closer. We'll have to erase it visually here. You saw something that was much closer. If you saw a result in statistics that was much closer, and we will calculate how to standardize this, like this, you saw something there, you might get something that is more probable by random chance. In your sample, you now saw 28% of students owning a pet, and you calculate a probability of the following of this. Now that is telling you that seeing 28% of students owning a pet in a sample where you would expect 25% of students owning a pet is likely by random chance, given 25% is true. So in this instance, you'd say, well, yeah, that's a little high, but I mean, seems possible by random chance. And that's what the p-value is telling us, whether or not this is likely. And I like to talk about like running a mile. If your friend says they can run a mile in 6 minutes, let's put that here visually. So your friend says to you, I can run a mile in 6 minutes. And then they go out to the track. There's your friend right here. And they run their mile. Gotta go 4 times around the track. 2, 3, 4. That was super quick. They run their mile. They run their mile in 6:02. And they told you they could run a mile in 6 minutes, which means the null hypothesis would mean that their true mile time is 6 minutes. They say, I can run a mile in 6 minutes on average. And so they run a mile in 6:02. Think about that. They didn't run a mile in 6 minutes. But you probably would not reject the null because you'd be like, well, that's close enough. It's still believable. This p-value here would probably be pretty high. You'd say, well, yeah, I continue to believe that you're a 6-minute mile runner. But what if it takes them 16 minutes? Well, in that instance, you'd be like, okay, that's some strong evidence that you are not a 6-minute mile runner. I am going to reject the null hypothesis because I have some good evidence at this point that you are not a 6-minute mile runner. You really tried hard and it took you 16 minutes and 2 seconds. I don't believe the null is true anymore. It's very unlikely that you would run your mile in 16 minutes and 2 seconds given you are a 6-minute mile runner. So I reject the null hypothesis right here. I like to use those examples right there because I think if we can bring it to how we kind of make judgment calls, then it makes a little more sense. How is the p-value used to reject or fail to reject the null? So we've got a pretty simple standard right here that we need to memorize. Very important right here. When the p-value is low, reject the null. When the p-value is high, just let it fly. That's what we say. And what do we mean low? We mean lower than alpha. So write that down right there. When the p-value is low, reject the null. When the p-value is high, just let it fly. Let it fly means don't reject it. Just don't reject, just fail to reject. Fail to reject simply means don't reject. I've always had my problems with that. It just means don't reject. Don't reject. So we either reject or we don't reject. I really think statistics should start saying that, but people do still say fail to reject. Think about this. I didn't go to the mall today. I failed to go to the mall today. That means you didn't do it. So when we say we failed to reject something, it just means we don't reject. It's just kind of a way that people used to talk as language evolves over time. So you either reject or you don't reject, and fail to reject means don't reject. If your p-value is less than alpha, you reject. So when you look at some of these things we've drawn out right here, you just look at this and you say, well, my p-value is high. I just let the null fly. I just let it be. I can continue to believe this. This was likely by random chance. Well, if we go back in time right here, we get the following result where we say, oh, my p-value is low. I reject the null. This looks unlikely by random chance. The p-value being low means unlikely to happen by random chance right there, as Ella put in the chat. So when the p-value is lower than alpha, we reject the null. Important thing to know right here, alpha is the standard by which we reject the null. And that's what we have right there. Let's go grab more of this info. Reasoning to test how many. Woo-hoo. Look at all that right there. Look at all that. We got this. How much time we got? Oh, we got 12 minutes. Oh, got a speed run faster. Whew. Okay, we can do this, everyone. We can do this. Trying to go slow but fast. It's contradictory. Reasoning of hypothesis testing. Checking conditions. Psh, we got this. You ready? Condition 1. Everyone knows condition 1. It's random. So condition 1 is random, which means we randomly select the individuals. This means they're independent from each other also. So we randomly select the individuals. We just call it the randomization condition. Look for that. Condition 1, random. There is no order to these, but random and 10% are always there, so I always call them the first two conditions. 10%, once again, is we sample less than 10%, but now we see the success-failure condition. The success-failure condition states that we need at least 10 successes and at least 10 failures if the null is true. So we have here NP0 and NQ0. And Q0 are both greater than or equal to 10. We need at least 10 successes, at least 10 failures. At least 10 successes, at least 10 failures. And next we see here, conditions to check for a mean, one sample t-test. We have the same first two conditions, random, 10%, and now we have the nearly normal again. The nearly normal is going to be that we either look at the shape of the distribution and see if we have a large enough sample size. So this looks normal. So as long as sample size is greater than 1, we're good. We have here, we can look at a normal quantile plot, normal probability plot, same thing. And if it looks straight, we're good. Or if the test of the goodness of fit has a p-value greater than 0.05. And that's because the null for it is that it's normal. And we don't want to reject that it's normal. We want to continue to believe that it's normal. I have more videos going over that in greater depth. I could definitely spend 15, 20 minutes talking about it, but usually it's not that big of a portion of the test. But I want to reiterate again that this is quantitative. You can't use things like bar charts to check it because bar charts are categorical. Statistical tests, calculations, and interpretations, mechanicals using the formula sheet. So let's go over this. We're going to be spending a good 4 or 5 minutes on this right here. Major thing. So let's take a look at the statistical tests. So we have two statistical tests right now to talk about. The two statistical tests are that Z, and this is the one proportion Z test. And please check out the other videos I have that go over this on a 20-minute review. I have a 20-minute review for each one of these statistical tests, doing them from start to finish. This is a speed run, so check out the other videos. Email me if you can't find them. They're in a playlist, and you'll find that they're the longer, one proportion Z test explanation. So we have right here the sample proportion minus the hypothesized proportion over the hypothesized proportion times the complement of the hypothesized proportion. If this is 0.8, this is 0.2. There's the speed run going a little bit quick right here. And then over the sample size. There we go, is the one proportion Z test. That is when you have categorical data. So it's very important to notice that this is categorical right here. And the next one is going to be quantitative. Like if we're asking questions about how much do students spend at pod, or how old are students, if it's a quantitative question. So Y bar, which is the sample mean, minus mu naught. That's a difference, just like the top one right there. And then we go next. Let's try to make it all on screen. And then we go S over square root of n right here. And this is if it's quantitative. S is the sample standard deviation. N is the sample size. And then we have T with n minus 1 degrees of freedom. Like the previous video, this is a one sample T confidence interval. So the degrees of freedom are n minus 1. And we also don't put a star on these because these are not for confidence intervals. These are the difference up top right here. So both of these just have a difference. How far away is our sample from our hypothesized value? And then we take that difference and we standardize it. And last but not least, that turns it into a standardized test statistic. This is step 2 for every hypothesis test, where we check the conditions and then we run it. The next thing we do is we take this T or Z, which I think it's mentioning next here on the sheet, is we're then going to find the p-value. So we can do this with online calculators, and we can do this with jump outputs. Let's talk about finding this p-value now and how to do that. How do you find this p-value from this test statistic? And this is step 3 right here. So when we find this p-value, we go to these Z's or these T's, and we take them and we plot them on their appropriate distribution. We'll see this in some jump output. So we take the distribution, and then we go right here and we plot our t. Like maybe we get a t of 0.6. So this is a t-score of 0.6, and that would be the standardized value from y bar 1, y bar minus mu naught over s over square root of n. Whatever we get from this is the t statistic with n minus 1 degrees of freedom. And we take this value right here and we plot it on the t curve. And then we have to shade the way that the alternative points. So if we are doing a test down here, the null will always have the equal sign, and we're testing a mean, so it's mu. We'd put right here. Let's go ahead and say we're testing to see if the average score of a test is 81. And then the alternative, whichever way it points, if we have mu greater than 81, like we want to see if students are scoring higher than 81, we shade to the right. Now, one important thing we need to know with the t is we always need to know the degrees of freedom. The t's shape of the distribution is based on the degrees of freedom. In this, we might have sampled, let's say, n equals to 210. So the degrees of freedom right here, df, equals to 209. That's how many degrees of freedom it has, and that is the shape of the distribution. As in, let's go ahead and take a look at this. We type in 209 right here, and we get the shape of the distribution. This right here is the does not equals test. We'll put in our value of, I think I put 0.55. We're not doing the does not equals test though. I put 0.6. Our t statistic is 0.6. Here's the less than test, and here's the greater than test. And notice we do get those p-values we talked about earlier, where this is 27.5% p-value, and this is 72.5%. And then if we double this, I'm trying to double in my head, we get 55. Oh, there's a little decimals we're not seeing in the background, but if you notice, we double this right here, and we get the two-tailed test. You can just see it visually as it doubles, and there's some extra decimals we're not seeing. So in this instance right here, you have to think, is this p-value high? Do we just let the null fly? And we do. The p-value here is high. We let the null fly, and we can see this in the jump output we saw earlier, where we did the exact same thing. There's the p-values in the test. All of these p-values are high. They're very similar, and that's the similar test statistic right here, where we see a very small test statistic. They're like z's, so that's very small. It's very close to 0, and we see here the hypothesized value. Let's go ahead and notate this. I think we're almost done. We got a speed run. We're going to put this in here. Okay. So the hypothesized value right here, we're just going to mark this output so we can see what it is. Talking about jump output. Hypothesized value is mu naught. Y bar, degrees of freedom are the df. You can see there n minus 1. Standard deviation is s. And we do have standard error over here. That's standard error, which is much easier to use if you calculate that. So the t statistic will be y bar minus mu naught over the standard error, which we are given on the right. And so that's a t with n minus 1 degrees of freedom. And we can calculate this pretty quickly by going right here and doing y bar. So we'll put the 4802.27 minus 48 that, divide by 86.272165, and we get the t statistic right there. So knowing how these are being calculated, the notation right here should help. That's mu naught, that's y bar. So actual estimate is the sample mean from the summary statistics. We're running out of time. We got this. We got to hurry up this speed run. They're all 30-minute speed runs today. Let's make sure, what else do we not cover right now? Relationships between hypothesis testing and confidence intervals. So when we do a hypothesis test in a confidence interval, knowing the threshold for the null is calculated. Yep. We've talked about rejecting and failing to reject the null. Good. Conclusions on the test. We talked about conclusions. So the last big thing I think to talk about right here is when we have a confidence interval. I lost track of my cursor. There we go. When we have a confidence interval, if you have a 95% confidence interval, it's the same thing as doing a two-tailed test where alpha is equal to 0.05. So a 95% confidence interval, 95% shaded in the middle, will come to the same conclusion as a two-tailed test. That is the worst two-tailed test I've ever drawn. The way it looks right there, it should look same on both sides. It's looking more similar now. So it should look the same on both sides. Better. So 95% confidence interval will come to the same conclusion. So let's say we were to ask somebody, how much do you think students spend at the pod market? And they hypothesize $50 a week. That's a lot of money. So they hypothesize $50. Well, if we were to make an interval from a sample and our interval were to come back with students spending on average somewhere between $10 and $30, because we found 20 as our sample mean, then think about this. 50 is outside our interval. 50 is way over here. And so since 50 is way outside the interval, the hypothesized value, what would you do? It's outside your 95% confidence interval, which means you would reject the value of 50. But if they had hypothesized a value like 20, or we don't want to say 20 because that's exactly what we saw in our sample. If they had hypothesized a value like 24, well, then the value of 24 is actually inside the interval, and you would fail to reject that because you would continue to believe it. You'd say, well, I don't reject that because it's inside my 95% confidence interval. And knowing the threshold for the null hypothesis is called the alpha. We talked about that. Alpha is when we reject or not reject the null. Understand the decisions. When the p-value is low, reject the null. When the p-value is high, just let it fly. Alpha is our level of significance. P-value and conclusions on the test, either reject or fail to reject. Woo! That's a good review right there, everybody. We will be back. Next speedrun starting up soon. Join in the video. Bye, everybody.